We are nearing the end of our discussion of amplifiers. So, the next couple of modules, we will first talk about the different designs of amplifiers that are there. And of course, this discussion will be incomplete, because really there are many designs. If we try to discuss all of those, it will become very boring. So, I will give you an idea of some, just to understand that several techniques can be used. And then in the next module, we are going to briefly talk about the amplifier that we have. So, right now we are discussing the different designs and materials that can be used to make oscillators and amplifiers. And as a recap, we have discussed this already. We have discussed two kinds of amplifiers. One is a multipass amplifier, in which the seed goes through the gain media multiple times, and this is used for very short pulses. No extra EOM or anything is used, so the pulses can remain short, but the power that you get, the energy that you get per pulse, the extent of amplification is not as much as one can get using a regenerative amplifier. And in the last couple of modules, we have discussed in as much detail as we could without getting into too much of instrumentation, the timing events that are there during regenerative amplification. And this is the one design that we have talked about, the design where the gain medium is in a cavity, and then the seed is switched in to the cavity by using a λ/4 plate. It is kept in the cavity by a combination of the same λ/4 plate and a Pockels cell, and then after the required number of round trips, it is switched outside the cavity, out of the cavity by the second Pockels cell. So, a design of a regenerative amplifier where we have two Pockels cells. But this is not the only possible design, there can be more. This is once again, now see, in this discussion of today, we are going to refer to optics journals very frequently, optics letters and all. So, this is an example of a regenerative amplifier design from 1993. That was the time when all this was being done. Even now it is being done, but we will see what is being done today. But whatever design we use now, even that sort of got defined this 20-25 years ago. So, here you see, here this paper where Moro is there, but Korn is also there. The interesting thing about this paper, I mean there are many interesting things, but one thing I would like to draw your attention to is that this is a collaboration between academia and industry. So, most of the authors, including Square, to whom several designs are ascribed, are from University of Michigan, Ann Arbor, but then there is one author who is from Clark MXR Incorporated, and that is a company that actually makes and markets lasers. And we will briefly talk about what kind of lasers Clark MXR is focusing on right now. But here this is an early report of an amplifier. Repetition rate is still 1 kilohertz, and what they had been able to do was they had taken 40 femtosecond pulses as seed. So, I would like to give you the feel of the numbers as well. These 40 femtosecond pulses were stretched to 372 picosecond, and then the specification of the grating is also given, and it was amplified to 0.7 millijoule energy. What is the energy we get out of our amplifier? 4 millijoules. So, this is not really as much as what we get today, and after compression you get 0.35 millijoule, 55 femtosecond transform limited pulses. So, it is not even 0.7 millijoule. 0.7 millijoule is what you get out of the region before it goes into the amplifier. There is always some loss at every stage, during stretching, during amplification, of course, it gets amplified, but maybe not to the extent that you would expect in the ideal case, and during compression also some loss is there. So, you see, before and after amplification, 0.7 millijoule to 0.35 millijoule. Half the power is actually, so before and after compression. After compression, half the power is gone. And if you look at the full width half max of the seed and that of the output, 40 femtosecond pulses were put in as seed and you get 55 femtosecond pulses. So, not only have you lost energy per pulse a little bit after compression, you have in the entire process you have not been able to get back the entire, you have not been able to get back to the pulse width that was there in the seed. So, I just like to draw your attention to this because when we do discussion without doing experiments, many times we are geared to think of the ideal case scenario, but ideal case scenario is very difficult to achieve. There is always some loss or the other. The challenge of course is to minimize the loss and get to near perfect, near ideal situations. So, let me show you the design, and here I would like you to, I have not animated the whole thing, not because it would take a long time, but because now that we have seen all these pulses passing and the polarization getting flipped and all that, I think we should now be able to work out what happens at every stage. So, I will start, I will get you started on how it works, but then let us see if we can do the rest of the path together. To start with, see what is there. I hope everybody can read. Can you read what is there? So, first of all, you have this argon ion laser. In 1993, argon ion laser was the state of the art. DPSS lasers were just about coming. Mostly people use argon ion laser, and even now there are people who work in imaging and all, sometimes they prefer argon ion laser because it has very sharp lines, but then it is very difficult to maintain, it goes bad, you have to change the tube, which is very, very expensive, and then when you have changed it, what do you do with that old tube? It takes up space in the lab. It is not easy to throw away a laser tube, it will burst, it is hazardous. So, anyway, that argon ion laser was used to pump the Tissefer oscillator. Output of the oscillator is 30 to 40 femtosecond, 3 nanojoule. Can you read these numbers? 3 nanojoule. Okay. Then it comes here, and I have not really read whether the polarization was vertical or horizontal, but to demonstrate the phenomenon, I have drawn it to be vertical. Okay. Vertical polarization. What is next in line? Thin film polarizer, TFP. What would happen when the vertically polarized light goes through the thin film polarizer? No, it is a polarizer, it is not a polarization rotator. So, it will go through provided it has a component that is allowed by the polarizer. It will not go through if there is no component. So, here the thin film polarizer is set so that it can pass vertically polarized light. So, this is an important thing to understand and remember. Polarizers sort of act as gates, they do not rotate the polarization, right. Do not get confused between a polarizer and a Pockels cell, and today we are going to talk about something else as well. Okay. After TFP there is a lambda by 2 plate, lambda by 2 plate would rotate the polarization by 90 degrees. After that we have something called a Faraday rotator. Well, the name sort of, at least the second word is self-explanatory, it will rotate. What will it rotate? It will rotate the polarization of the laser. Okay. And what is a Faraday rotator? What is the difference between a Faraday rotator and Pockels cell? They use two different effects. Pockels cell uses Pockels effect, and Faraday rotator obviously utilizes Faraday effect. Okay. Pockels and Faraday are names of very eminent scientists. So, we have already discussed Pockels cells where you apply an electric field and that causes rotation of polarization. In a Faraday rotator you apply a magnetic field. You still apply an electric field which causes a magnetic field, and it is a magnetic field that causes the rotation. Right now we do not need to get into the nitty-gritty of whether they are interchangeable or whether you want to use this or you want to use that. Right now let us just take it like that, there is a magnetic field. As long as the power is on like it is now, it is going to rotate the polarization, and in this case by 90 degrees. So, what happens? when the vertically polarized light reaches the thin film polarizer, which is set to vertical polarization, it will pass through. Then when it goes to lambda by 2, then what happens? It will get rotated by 90 degrees. So, vertical polarization becomes horizontal polarization. Then when it goes to the Faraday rotator, it is turned back to vertical polarization. Why we are doing this, we will understand in a while. Then what happens is, it goes through the thin film polarizer. So, see, the design is such that you use the same path until a point, and then there is a branching. From the second thin film polarizer that is there, the light beam has a choice. It can either go straight and enter the stretcher, or it can get reflected and go into the compressor. Okay. That will be determined by the polarization. This thin film polarizer is once again set to vertical. Okay. So, vertical polarization will go through, and if it goes through, then it goes to the stretcher and gets stretched. However, if this was horizontally polarized, it would be reflected by this thin film polarizer and would go into the compressor. That is what happens after amplification. Okay. For now, it goes straight, and I have not drawn its path all the way to the stretcher, but you can understand it goes in. This is a mirror. From the mirror, it goes to the grating, first grating, gets dispersed, goes to the concave mirror, which sort of focuses it on to a second grating, plane mirror, then retraces its path, comes back here, and then goes back all the way. Okay. So, here there is an alignment where it is retracing its path, and this alignment is actually more difficult than what we have discussed for the amplifier earlier. Because now you have two parameters, not only do you have to take care of the beam going in one direction, the beam coming back should actually go through the same path. Of course, people working with lasers, for them it is not so unusual, because when you have a laser, you have two mirrors and the gain medium, to and fro beams have to have the same path. So, I do not know whether that was the reason why it was designed this way, but this was what it is in most early amplifiers, and maybe even some modern ones. Because one thing it does is that it can use the same pieces of optics multiple times for doing different things. Okay. So, it comes back, and when it comes back, it still retains the vertical polarization. So, it will go through, yeah, and when it goes through, oops, sorry, that was too fast. When it goes through, what will happen? Thin film polarization polarizer lets it through. Faraday rotator is now off. So, Faraday rotator was on at the beginning, right? Right after the beam passes through, it is turned off. So, now it is not going to rotate the polarization anymore. So, if it does not rotate the polarization anymore, what will happen? At lambda by 2 plate, it comes as a vertically polarized light and turns by, the polarization is turned by 90 degrees, it becomes horizontally polarized. Now, what will happen when the beam retraces its path to this thin film polarizer? Will it get through? No, because that polarizer, as we discussed earlier, is set to vertical, right. So, now it will come to the thin film polarizer, it will be reflected, and after this I have not drawn the path. Let us see, without the aid of those arrows and donuts, if we can figure out what is going on in the rest of the cavity. Okay. So, this is how the beam is stretched and injected into the cavity, and we have to remember the polarization now. What is the polarization? Vertical, horizontal? Horizontal, right. So, horizontally polarized light goes from thin film polarizer, first plane mirror, second plane mirror, thin film polarizer again, and then it has to be reflected. So, if it is to be reflected, what is the polarization that this TFP allows to go through? Vertical. Understood? So, horizontal polarization is going to be reflected into the Pockels cell. Okay. Pockels cell is on. So, while coming back, it will become vertically polarized. So, now it will pass through the thin film polarizer, and then it hits this curved mirror, which focuses it onto the gain medium, through the gain medium onto the high reflector here, and this entire arrangement is pumped by a Q switch Nd:YAG laser, as we had discussed yesterday, 100 200 nanosecond full width of maximum, big pulses. Understood? So, vertical polarization all the way. Now, it does whatever number of trips it has to do, and you see there are only 3 mirrors. So, after the required number of trips, then this focal cell is turned on again. So, vertical goes in, turns by 45 degrees, while coming back turns by 45 degrees again. So, now when it reaches this thin film polarizer, once again it is horizontal. So, it will not get through. So, horizontally polarized beam comes back to this thin film polarizer. Okay. What will happen? Does this thin film polarizer allow the horizontally polarized light to go through, or does it reflect? This is what we need to remember. Okay. Go back to the, it will reflect, right? Remember, we started with vertical polarization and that light went through. So, horizontally polarized light will be reflected, turns by 90 degrees. Okay. Now, do we want the Faraday rotator on or off? Because now what is the next step? It should go in this direction, isn't it? It should go in this direction into the compressor. So, should we turn the Faraday rotator on or off? Or should it remain off? Should we turn it on? Should it remain off? Remember what happened the first time? When the Faraday rotator was on, it became vertical once again and passed through this thin film polarizer, went to stretcher. Do you want that to happen? No. So, you do not switch on the Faraday rotator at this stage. So, then what will happen? It will still remain horizontally polarized, hit this thin film polarizer, get reflected into the compressor, gets compressed, 55 femtosecond, 350 microjoule pulses come out at the rate of 1 kilohertz. What is it that determines that the repetition rate is 1 kilohertz? Where did the 1 kilohertz come from? Yes? Yes. This Q switched Nd:YAG laser is operated at 1 kilohertz. So, see, the way it works is that you need a timing circuit. A timing circuit is some electronic board that takes input from the YAG laser, from the oscillator, and can drive all these focal cell and your Faraday rotator. Okay. So, it is very important to do a precise timing. That is where electronics comes in big time. So, of course, nowadays up to this stage nobody builds an amplifier, to be very honest, because amplifiers with as short pulse as you want are available in the market, but you might have to fix one. You have an amplifier in your lab. In many places I do not think it is any better abroad. Service engineers always take a lot of time to come, does not matter which country you are in, unless maybe you are in Saudi Arabia or some such place. So, sometimes you might be required to fix a laser when you are a postdoc or when you have your own lab. Sometimes in some labs the old homemade oscillators and amplifiers are still working. So, if you happen to land in one such lab, in a lab like that, you might have to use it. So, it is better that you know. Okay. So, this is the design of a regenerative amplifier with a single EOM, but then when I say single EOM, I am cheating a little bit, because I am sort of not telling you that there is also a Faraday rotator with that. Great. Next, one more design, and we will go a little quicker now. I wanted to show this primarily because all this time we were talking about people who are laser physicists or engineers and all. This laser is made, it was built in the lab of a true blue physical chemist, Robin Hochstrasser. Okay. And just look at the parameters, 18 femtoseconds, shorter pulse. 18 femtosecond pulses from a self-Mortlock tie sapphire laser were amplified to 60 microjoule. So, amplification is not so much. right, of energy at 4.9 kilohertz. So, the laser they used to pump the region had a repetition rate of 4.9 kilohertz. With sharp pulse amplification in a tie-sapphire regenerative system, after compression 30 to 35 femtosecond near transform limited pulses are obtained. So, once again you see, you start with 18 femtosecond seed, you end up with 30-35 femtosecond amplified pulses. So, that is why whenever you get an amplifier, you want the oscillator associated with it to have as short pulse width as possible. Okay? Right. And this is the design. I will not discuss it in more detail, but I encourage you to try and work out the path of the beam in this one yourself. Let this be a homework. Okay? And I just like to draw your attention to this fact that here they are using a prism pair to add some more of compression so that the smallest pulse can be obtained. And sometimes even this is not enough, you might have to use extra cavity prism pairs. Okay. Now, let us move to another kind of system. All this time we have been talking about titanium sapphire and titanium sapphire alone. So, you might have given the idea that there is nothing in the world other than Ti-sapphire with which your ultrafast lasers are made. That is not the case. Another material that is used is called alexandrite. Alexandrite is chromium doped BeAl2O4. The range of tunability, range of emission is 700 to 830 nanometer. In fact, I think in 1979 or so, the first tunable laser solid state was made using alexandrite. So, it has been there in the market for a long time. But why is it that Ti-sapphire is so popular, alexandrite is not so popular? The answer is sort of there on this slide. Just see the bottom line. This paper we are discussing by Major and co-workers was published in Optics Express, which year? Which year? Oh, the year is not even there. I think 2012, if I am not much mistaken. When the DOI is given, 2012. Even in 2012, read the first line, generation of 170 femtosecond pulses at 755 nanometer from a Carl lens mode locked alexandrite laser was demonstrated. Output power is 780 milliwatt, more or less like what we have in our tsunami, actually less than that. And to the best of our knowledge, these are the shortest pulses that have been produced from a mode locked alexandrite laser to date. So, even to go down to 170 femtosecond, which is not a big deal with Ti-sapphire at all, that has been achieved only 3-4 years ago. So, that is why Ti-sapphire is much more popular, but alexandrite is also used for several reasons. And I want to discuss alexandrite especially because I want to talk about an interesting architecture. But before we go there, this is your, well, since this paper was published in this millennium, the figures are in color. Okay. So, you see even these people, like what Hochstresser's group did in 1993, they have used intercavity prism pair. In fact, in the photograph, this is the alexandrite rod. And here you can see this prism, can't you? You cannot see the other one, but you can see one. Now, what do you get? This is the spectrum of the pulse. What is the full width of maximum? 3.6 nanometer, actually very narrow. It is sort of like our diode lasers. And full width of maximum of the pulse, well, how much is it? 170 femtosecond. And that is the best one can do using an alexandrite laser. But think of it, this would be an interesting or useful laser if you want to do TCSPs, isn't it? Spectral width is narrow. The problem with using Ti-sapphire laser for excitation or doing microscopy is that it is a broadband laser. Many times if your laser is spectrally very narrow, you can and if it is tunable, then you can excite molecules in different environments. With trisapphire, that shorter the pulse, that advantage is compromised to a greater extent, because spectrum is very wide. Here the spectrum is narrow. So, that is actually an advantage. Disadvantage is you cannot go less than 170 femtosecond. Okay, so this is the Alexandrite laser, and then I want to show you something interesting here. Then what we will discuss next couple of minutes is actually a little bit of digression, in the sense that it is not ultrafast laser, it is a CW laser. But I still wanted to talk about it because it is an interesting design, and I think that this could perhaps be one of the important designs for future, where people might be able to make ultrafast lasers using that design, and you will see why that design is fascinating. So, here this paper is from last year, and this is actually a conference proceedings of SPIs. SPI has this Photonics West conference in San Francisco every year in the month of February. There are several smaller conferences in it. So, this one I think was part of LASE, LASE, which is a laser conference. So, there LED pumped Alexandrite lasers were demonstrated. So, see, until now we have been talking about DPSS pumped lasers, right. If you can use LED, the cost as well as operational issues go down by orders of magnitude, right. And now LEDs are so commonplace, these are LEDs, the light we have in this room. Okay. Everybody is familiar with LED, they are everywhere. So, what they had done is, they had taken, so this is the LED right here. I have forgotten the size, I think it is 1 centimeter by 1 centimeter. They had taken LEDs that gave out emission which peaked at 450 nanometer. That emission was concentrated by using something called a luminescent concentrator. I will discuss how it works, and these concentrators are very much topic of contemporary research. Only yesterday we had visit by an inorganic chemist who talked a little bit about how he is trying to make concentrators. We will come to that. Now, this concentrator material that is used is cerium YAG, and emission of cerium YAG is at 550 nanometer. Emission of LED is peaked at 450 nanometer, and it overlaps very strongly with the absorption spectrum of cerium YAG, which has a maximum at 460 or somewhere like that. Then emission of the cerium YAG is at, you see, very broad emission, 550 or so, and this emission spectrum has a very strong overlap with the absorption spectrum of Alexandrite. So, the idea is use an LED, excite cerium YAG, it will emit, somehow concentrate that emission and deliver it to Alexandrite. Now, Alexandrite can emit. Okay. So, we will take a break now, and we will come back and we will start our discussion from how a luminescent concentrator works.